I'm Eric from the University of Maryland. Today I'll be presenting some work on certain quirks of neural models and how these quirks, which we call pathologies, can have downstream impacts on your interpretation methods. This is joint work with my fantastic collaborators. Shurfang did most of the legwork for this project, but unfortunately wasn't able to be here. So as background, we know neural networks make great text classifiers. And by text classification here, I'm speaking quite broadly, including things like reading comprehension, where I want to output a beginning and an end of span, whenever I'm picking from a fixed number of classes. But are these models doing the right things? So this is, of course, a more philosophical question, but how can we understand and interpret their inner workings? So a really common way to do interpretation is through saliency maps. Essentially, what we want to do is highlight which words are important for the model's prediction. For example, here we see the word money is highlighted in red, indicating it's probably important to the model, which kind of makes sense. If you look at the final sentence, it has money as a direct match, and it's able to successfully pick Colorado Springs experiments out of the paragraph. Now, how do we actually generate these importance values for each word? So a simple way is called leave one out. Basically what I do is I just leave a word out from the input. For example, I remove what, and I measure how much the confidence goes down. And by confidence, I mean maybe the output of your softmax, whatever the probability of the answer is. And we see it drops from 78 to 68, so it gets kind of like a light highlight. We can keep doing this. We see did is a bit less of a drop. And we remove the word money, it goes from 78 to 48, so it gets a very dark highlight. And then once we consider each word independently and kind of put them together into a final saliency map. So of course this is quite slow, especially for long inputs. So the most common way to do interpretation is probably using the input gradient. Essentially what I do is I backprop from my classifier f into the word vector v, and then I multiply that gradient by the word vector itself. This gives me a final importance value for each word, and I can do it in a single backward pass of the model. So we'll use this gradient approximation in all of our experiments. So the central idea of our work is this process called input reduction. Essentially, the question we're asking is, what happens if we remove the unimportant words? So for example, we want to take away the features the model doesn't need, and hopefully the important features are the ones that are left. And we'll do so keeping the model prediction the same. So the model has not changed its answer. We'll just keep removing words until it's about to do so. So let's walk through an example of how this works. So we'll first remove the word spend, which is the least important word according to the interpretation. Interestingly, the word money, which was the most important, is the least important on this new interpretation on the shorter input. And we can keep doing this process, removing on. Eventually, we get to just the question did, and the model predicts the correct answer, Colorado Springs experiments, with a confidence of 91%. So the prediction is the same, crucially, and our intuition completely failed. Money, which was the important word, is not the one that's left. It's did. And the model confidence is extremely high, even for the correct answer, yet the question is just the word did. So does this hold for other data sets? And let's explore this further. So we looked at squad. Here's the example we just saw. We also looked at VQA. What color is the flower can be reduced to just flower without changing the prediction for yellow. And we can reduce in SNLI the hypothesis two man is dancing on the street to just dancing without changing the model's prediction of contradiction. So these are like three toy examples. Does this hold more generally for the model? So to scale this up, what we do is we're going to run this input reduction process for the entire validation set. So we iteratively remove the least important word, regenerating the interpretation, and making sure the model prediction has not changed. So we stop this input reduction process immediately before the model is about to change its prediction. And what we find, we plot here the histogram of the question lengths for squad, for example, seen on the left. In blue is the original. It's distributed between about 5 and 20 with an average of 11.5. Yet you can reduce it to just 2.3 words on average without changing the model's prediction. The same holds for SNLI and VQA. But what about the model's confidence? It must have dropped on these short examples, right? Yet the model's confidence looks about the exact same. So here's a density distribution plotting the confidence from 0 to 1. We see there's basically a strong overlap between the original and the reduced. On VQA, it even goes up a bit at the end. So what's going on here? We started with a a completely reasonable interpretation method, what looked to be a completely reasonable interpretation method, yet we saw these completely ridiculous results. So we wanted to investigate, is this behavior really unreasonable from the model? Maybe these tasks are just kind of simple, maybe they have a lot of filler words, and you can actually solve them using just 2 or 3 words. So to do so, we ran a simple human experiment. On the left, we showed humans, on the left column, we showed humans the original input and plotted their accuracy for different tasks, breaking SNLI into its 3 different classes. And we see humans are getting about 80.58, for example, on squad. On the reduced inputs, these short nonsensical ones appearing, the humans are getting 31.7. So you see the significant drop in human performance, yet the model is still getting the answer. It's still predicting its same answer, so it's getting high accuracy. We wanted to investigate this further, saying, do these inputs look completely random to humans? So to do so, we set up this simple preference study. We're given the question, what did Tesla spend Astor's money on? And we give them either did, which is the example that's been reduced using input reduction, using the trained model, or spend, which has been randomly reduced. It just is selected from the question to match the length of the gradient-based reduce example. And we report how often humans pick the one from the trained model versus the random one, and their choice is about 50-50. So humans find these examples uninformative, and not only are they uninformative to solve the actual task, they appear random to humans. So how did input reduction lead to these extremely strange results? So let's take a step back and look at results from literature and see if they can explain this phenomena. So Guo et al., IAC Mail 2017, talk about model overconfidence. In short, they show that models on average predict much higher confidence than they have in accuracy. So for instance, on CFAR 100, they predict close to 90% confidence, yet their accuracy is closer to 60. Though this doesn't talk about these kind of nonsensical inputs, like this question did. So overconfidence doesn't quite explain the results we're looking for. Instead, these reduced examples better fit the definition of what's called rubbish examples. Rubbish examples are inputs which a human would classify not belonging to any class. So for example, here we see these static images, just kind of static noise, and the model predicts horse every time the box is highlighted in yellow. So these reduced inputs kind of fit this definition of rubbish examples. A human would say, okay, this doesn't really belong to any class, yet the model's predicting high confidence. So now we've narrowed our question. So how did input reduction lead to rubbish examples? So let's take a look at a specific example to understand why. So here we're given a paragraph from Wikipedia in Squad that says, the Panthers use San Jose State practice facility and stayed at the San Jose Marriott. The Broncos practiced at Stanford University and stayed at the Santa Clara Marriott. And note the question asked about the Broncos practice facility. So note how important the word Broncos is. Without it, if it said Panthers instead, you would pick San Jose State. So it's crucial for disambiguating the answer. Yet the interpretation assigns it the least importance. So it's actually removed in the first step of input reduction. So after just one step of this input reduction process, we already have an example which a human would classify as rubbish example. They don't know which answer to pick. Yet look at the model's confidence. It has not dropped at all. So even though you can't correctly disambiguate the answer, the model is still predicting with high confidence. The takeaway from this should be that the decrease in confidence, which is what these interpretation methods are relying on, does not align with the human perceived importance of the word. In other words, a model's confidence is not a good measure of its uncertainty. A model can be extremely confident, yet have high uncertainty in its answer. So this explains this kind of high confidence on these ridiculous, nonsensical inputs. Why didn't the interpretation method result in the words which we originally deemed important? If you remember, we had the word money, and it reduced to did. Why didn't money come out from that? So to understand that problem, let's take a look at another example in detail. So just focus on the question. We see the word advertisement is highlighted in dark red. We'll run input reduction now. We first remove the word contest. Basically, nothing changes. This is quite intuitive. But then we remove the word QuickBooks. We see advertisement goes from the most important word to the least important, as we saw before. If we keep running this, we see the heat map just keeps shifting around. So this kind of instability in your interpretation is caused by a few things. So one is the interpretation considers each word independently, like we talked about before. Yet the model is able to learn the interdependencies between the features. And also, your model is being interpreted using a gradient-based approximation, which is assuming it's linear, as if it's some sort of bag of words model. So it's neglecting these higher order features the model is able to learn in deep ILSTMs, for example. So we saw two failures, basically. One is due to model overconfidence, which is a failure in the actual model itself. The other one is a failure in the interpretation method, which is neglecting kind of the interdependencies between features. So we'll try to address just the model issue and leave fixing the interpretation to future work. So to address the model issue, the ideal behavior we want out of our models is to say, I don't know, on these kind of nonsensical inputs like did, which is what a human would do. Yet it doesn't really have a way to do that. The best proxy we have is to output like a uniform distribution over classes. So for example, like a random guess. So to optimize that, we'll use this two-term objective. On the left, we have maximum likelihood, just standard log of the correct class. And on the right, we have an entropy term. The entropy term is run on this data set x tilde, which is the reduced set of training examples. So basically what we'll do in practice is we'll first train a model till convergence, then with standard maximum likelihood training, then we'll reduce the entire training set using the input reduction process, and then we'll fine tune with this objective, with the standard maximum likelihood and an entropy objective. So when you rerun the input reduction process, the model's answer changes much quicker. So it stops much earlier. For example, we see the question instead of did, now it's spend, asked, or money on, which to a human makes much more sense. The confidence has also significantly dropped. Same holds for VQA. We see what color is flower. And for SNLI, we see two-man dancing. And two-man is the keyword you need to predict contradiction because the hypothesis says man and woman. So this crucially didn't affect the model accuracy. We even saw a small increase for squad. Yet what we care about is this reduced length. It went from about 2 words to about 5. So we reran the human studies, and it showed the examples are significantly more meaningful. So human accuracy increased, and they were now preferring these examples to the random ones. So let's conclude and talk about and summarize what we talked about. So we saw neural models are extremely overconfident. So we suspect this results from poor uncertainty estimates coming out of maximum likelihood training. So there's nothing in the maximum likelihood objective that's trying to encourage your confidence to be calibrated in any way or to be reasonable on out-of-domain inputs. This can cause difficulties for interpretation because confidence is not a good measure of your model's uncertainty. You need better, more principled approaches to figuring out how uncertain your model is. We saw entropy regularization can help mitigate this problem by maximizing the output distribution's entropy on the reduced examples. We also saw interpretations make this gradient-based approximation. So it's assuming your model is sort of linear, as if it's a bag of words. And this neglects these higher order terms that are in your model. So future work can perhaps integrate the Hessian into your model or other higher order terms. And to finish, I'll make 2 shameless plugs. So we're running a competition on December 15th, trying to develop robust question answering models. Check out quanta.org. Also, I'm applying to PhD school, so please take me as your student. Thank you.
So we have some time for questions. Please step up to the mic, or if you're here, I can hang it over.
It's a very interesting paper. So as we all know that there's another line of the research called adversarial examples, right? So in adversarial example, basically that you have a very small perturbation with your input. For example, remove one mode or just add one word, you will completely change your class's prediction, right? So basically this is kind of opposite. So we try to keep the class and same, but at the same time we want to change the input to see how it will change the result, right? So the interesting here is that so basically it seems like the neural model it's learn very different feature as a human do. And so in the other sense that it seems like in terms of adversarial example, it's also very sensitive to the input change when we change the class prediction. So have you think about how to collect this work with adversarial examples?
Yeah. I guess I would, yeah, so if you use the definition like you talked about where, I guess in images people say like, okay, it must be constrained in this like norm ball or something. I guess it doesn't fit exactly like you said, the definition of adversarial examples. Instead, in the paper, we called them like accidentally adversarial. And we called that because imagine maybe someone's on Google, they type in the word did and hit enter too early. All of a sudden, one of the documents shoots to the top as extremely confident that that's the one they're looking for or something. Similar things could hold in like speech recognition, maybe it drops a bunch of words or something. So I agree, it's an interesting like idea for doing adversarial examples, yeah.
Next question.
So I'm wondering, it seems like you're making it robust to this particular class of rubbish examples, which are these reduced ones. Do you have any sense of how robust it is to other types of bad examples? Or are you, or even back to the original class, are you actually looking at a validation set where these are rubbish examples that weren't trained on, that the model wasn't trained on?
Sorry, I think I'm confused. Like what other types of, I guess, examples are you thinking about? Like random words or something?
Yeah, like either, yeah.
Some of the experiments we've run are like just trying random word inputs, which for some tasks seems to trigger high confidence some of the time. So you might not need input reduction if you want to generate these kind of nonsensical inputs which trigger high confidence. You can just kind of sample words from your vocabulary. But in terms of like evaluating robustness, we haven't really explored other things, though it's interesting for exploring further. Yeah.
Thank you.
Yeah.
One quick question while the next speaker gets set up.
You mentioned that the leave one out method is problematic because it's very checks one word at a time. Do you have better methods that you think are more robust?
Do I have a better method? No, I don't. Not yet. Yeah, I guess, yeah. Thinking about it more, yeah.
All right, let's thank the speaker once again.